Okay, so we talk about, we are almost end of the lecture. So, we talk about computational complexity. So, what is feasible, what is not feasible in polynomial time. So for most of the algorithm we have solved, we can we have a polynomial time solution for that. So, we have a, so now this class we want to discuss when we cannot do that. I mean when we cannot, there are many problems which cannot be solved by polynomial times. So we will talk about complexity classes. So basically we talk about three complexity classes, P, X and R. So these are basically complexity classes. So what is P? P is basically the set of all problems which are solvable in polynomial time. So it will take at most polynomial time. So P is basically problems which are solvable in at most polynomial time, in polynomial time. So polynomial time means the complexity is some n to the power c, where c is a constant. So this is less than equal to at most. So at most polynomial time. So less than equal to. Okay, so this is the class where we consider all the problems which can be solved in polynomial time. We have seen many problems so far in our lecture. So most of them we have seen solved in polynomial time, but today we want to know there are a hell lot of problems which cannot be solved in polynomial time. Okay. So the second class is X, which is basically problem solving in exponential time, problems solvable in at most less than equal to exponential time. That is why exp exponential time. So this is at most, so less than equal to. So this is the class where we put all the problems which is which will take exponential time. So exponential time in particular we will look at 2 to the power n to the power c time. So where n is a constant. So this is the time complexity for such a problem. So for example, so all the polynomial times algorithm is subset of this. Okay. So if we want to draw a picture, so almost all problems are belongs to in this class. So almost every problems are in this class. So if you want to draw a picture, here this is a P and this is X, exponential time algorithm. Now what do you want? We want to bring the problem from here to here. So that we did for say dynamic programming problem. We know this is exponential time algorithm, but we try to solve it in polynomial time by the help of memoization. So all this technique we use. So this is our, we want to bring the problem which we know it is a exponential time algorithm. We want to bring it here. So P is basically, so P is a subset of X. Okay. We have a other picture to draw that. This is not a very good picture to explain this. So there are another class. So we want to draw it in different way. So in a line. So like this. So this is basically this is basically we denote by computational difficulty. Computational difficulties. Okay. So, here up to this is P, that means these are easy problem which can be solvable by polynomial time algorithm, polynomial time, and then we have another one which we will explain, and we have x exponential time, and then we have here what is called R. R is another complexity class. So, R is we will explain R. So, what is R? R is basically problem which are solvable in finite time. So, problems. So, this is the set of all problems which are solvable in finite time. Okay. So, this is basically R set. So, R stands for this problem. R is the collection of all problems which can be solved in finite time. So, this set is P, which is easy problem. This set is XP, which is exponential time algorithm, and this set is basically R. So, which are the problem which can be solved in finite time. I mean, so we should have a finite machine which can give us a solved state. So, anyway, I am not going to that theoretical details, and there are other problems which are here. So, these are basically problems which cannot be solved in finite time. So, this will take infinite time. So, these are called uncomputable problem or undecidable problem. Okay. So, these are basically uncomputable problem, because this problem we cannot get a solution of this problem in a finite time. So, this problem is undecidable. So, this problem has no solution in a finite time. Okay. In fact, most of the problem are in this range. We will prove that most of the problem are in this range which are uncomputable. Okay. Now, let us take some example of these classes, example of problems which belongs to these classes. So, let us take example of these classes. So, we want to take an example of polynomial time algorithm. We have seen many. One of this is a negative weight cycle. So, to determine, so we have given a graph, we want to determine whether there is a negative weight cycle or not. So, this is basically negative weight cycle detection. So, we know this is in P, because we know a algorithm which is Bell-Manford algorithm whose time complexity is order of V into E. So, that is polynomial time algorithm. So, this is a example of P, I mean a problem which is polynomial time. Now, we want to have an example of exponential time algorithm, that is n cross n chess problem. This is belongs to X, exponential time algorithm. What is this? This is basically we have given a position of a chess. So, we are playing chess. So, we have given a position of a chess, position of this chess. Now, we want to decide whether white win or not. So, this is the problem. So, this problem has no polynomial time algorithm to solve this problem. So, this problem is exponential time. So, we can try for all possible move, and then so this is basically exponential time algorithm, exponential time problem. So, this belongs to this. So, the problem is given a, so who win, white, like white or black, who wins from given chessboard configuration, given board configuration. So, we have given a position of the board. Now, we want to take the decision whether white win or not. So, this is the problem. So, this problem is hard, even this is hard for 8 cross 8 chessboard. This is even hard for 8 cross 8 chessboard. So, that means there is no polynomial time algorithm to solve this problem. So, this problem is hard problem. So, this is basically belongs to exponential class and it is not in P. Even this 8 by 8 chess also, this is not in P. That means, we are not having a polynomial time algorithm to solve this problem. So, this is a typical, this is an example of exponential time algorithm. Okay, so, another exponential time algorithm is Tetris. Another exponential time problem, which is basically Tetris. What is Tetris? We have a board like this is a game. So, we have a board, this is a computer game and we have some blocks. So, blocks are of this form, say this type, maybe this type of thing. We may have this type block, we may have this type blocks. So, these are the types of blocks. We have seen this is also one type of blocks. So, there are all possible blocks and then these blocks are falling and we have, suppose we have given some situation like this, say like this. Like this. So, we have given some position of the board and so we have given the board and we have given a sequence of blocks. Now, we have to decide whether we will survive or not, whether we will stuck or not, either we will survive or not. So, if there is a matching, then this will vanish, something like that. So, when we will not survive, if it is touch the top of the board. So, the problem is, Tetris problem is, so given this G comma S, S is basically a sequence of these blocks. So, given a board, given a game board, and a piece of sequence. I mean, we have these blocks, we have these shapes. Can we survive? This is the question, this is the problem. So, can we survive? So, that means, can we just this is coming like this. So, it will fall like this. So, if it is, if this row, one row is complete, then it will just vanish like this. So, this game we have seen, this is a computer game, this is called Tetris game. So, this is hard. So, there is no polynomial time algorithm to solve this, to answer this question whether we survive or not. So, this is hard. So, Tetris is this is hard. Okay. So, this is another example, but we do not know whether this is belongs to P or not. I mean, this has no I mean, we do not know whether this is belongs to P or not. There is no algorithm so far whether this can check that given this whether we can survive. Okay. So, so that is we do not know. whether, so this we do not know, this is a question mark. Okay. So this is another example of the exponential time algorithm. So Tetris is suppose here, Tetris. So we do not know, I mean this is exponential time algorithm, but we will see, I mean it is also NP, we have not defined NP, we will talk about NP. So, so now let us talk about R, some example of the problems which are say not in R. Say for example, halting problem. Halting problem. So, what is a halting problem? So, we have given a computer program and the question is, does it ever halt? So, given a computer program, the question is, does it ever halt, stop actually, that means stop. Okay. So, this is the problem. Problem is, we have given a computer program, the question is, does it ever halt, does it ever stop. So, this has no finite, there is no algorithm to solve this problem in finite time for all input. There maybe for certain input we can say the answer is yes or no, but in general for all input it is, there is no such algorithm we can say that the answer of this question. So, that is why this does not belongs to R. So, that means there is no algorithm which can tell, given a arbitrary program, whether it will halt or not in a finite number of in a finite time. Obviously, in infinite time we can say, because we can run the code and it may go up to infinite time. So, at infinite time we have the answer whether it will, but for finite, because for infinite we can run the show, we can run the code, we can run the program and then we can see. So, but there is no program. So, this is basically uncomputable, because this is not in R. So, that means no algorithm, there is no algorithm solve it correctly in finite time for any input, in finite time for on any input, any. There may be certain input we can say yes, but in general for an arbitrary input there is no algorithm which can say that. So, this problem is not belongs to R. So, this problem is uncomputable problem. So, this problem may take in general infinite time. Okay. So, now our claim is most of the decision problem is uncomputable. Most of the decision problem does not belongs to R. So, this is our next conclusion. So, most of the decision problem. So, what is decision problem? We will explain. So, where the like problem we have discussed, what is there any negative weight cycle? So, this answer is yes or no. So, this is decision problem. Okay, this program will given a program, computer program, whether it will halt or not, yes or no. So, this is called decision problem. So, we have two answer, yes or no. So, every problem has a decision version of it, most of the problem has is decision version. So, most of the decision problems are uncomputable, that means not in R, that means not in R. Most of the decision problems are not in R. Okay. So, what is a decision problem? Decision problem means the answer is yes or no. So, that means does this program hold, yes or no. Okay. So, given a board, play board and a sequence of this sequence in Tetris, whether we can survive, yes or no. So, given a position of the chess, given a position of the chess board, whether white wins or not. So, this is all are decision problem. So, every problem, most of the problem has a decision version of it. So, we want to see why this is true. I mean, almost all of the decision problem is does not belongs to R. So, why it is true? Because, so if it is in say if it can be solved in finite machine. So, there is a program. So, computer program. So, program basically. So, program either in C, C++, Python, anything, but ultimately it will convert into ASCII and ultimately it will convert into machine code. So, machine code is basically 0-1 bits, because computer can understand only the 0-1 bits. So, it is ultimately converted into 0-1 bits. So, basically it is a binary string. So, this is basically a binary string. So, every program is ultimately converting into binary string. Now, if you have a binary string 0-1 bits, so that is basically a natural number. So, by every binary string we can think of a natural number, set of natural number. Natural number means 1, 2, 3, 4 this set. Okay. This is basically set 1, 2, 3, 4 up to infinity, natural number. So, every binary string can be converted into natural number. Okay. So, every program is a basically converting into a natural number. So, if we have a program, it is basically a natural number, there is a 1-to-1 correspondence. Okay. Now, we would like to see the decision problem, how we can see the decision problem. So, decision problem is basically, so decision problem is basically it is a function from binary string to 0-1, because we have a we have a problem, we have to say yes or no. So, it is a basically a function from binary string to yes or no. That means yes or no, that means 0 or 1, we can say yes is 0 like this. This is our convention. So, this is a function from a binary string to yes or no. Okay. Now, how many such function is possible? So, that we have to see. So, how many such function are possible? So, basically, so we will keep this. This is R. Okay. So, basically we have given a string and then we are converting into binary. So, this is a function from a binary string to 0-1. So, how many such function is possible? In other word, we can say, we can consider this as a table. So, we have all possible binary string. Binary string can be mapping from to the natural number. These are all possible binary string. Then we have a say 0, 1, 0. This is one function. So, how many such functions are possible? If this string is finite, then it is, if there are n bits, then 2 to the power n, because each of the field can be filled by n ways, 2 ways. So, 2 to the power n, but there are n possibilities. I mean, this is capital N. So, there are infinite number of bits. So, this is basically infinite, size is infinite. Okay. So, there are such function is infinite, uncountable, infinite number of such functions are possible. So, this is basically R set. This is basically R set of all possible real numbers. So, this is a uncountably many set. Okay. So, our decision problem is belongs to R set, and our program, computer program is belongs to n set. So, now R is far greater than n. So, that means we have very less number of program for our solution, because each program will give a solution of a particular problem. Okay. And we have uncountably many problems, and we have only countably many programs exist. So, there are many problems which are unsolvable, because this set is very much bigger than this set. So, there are many problems which are basically unsolvable. So, this is the proof sort of where this is basically telling us the decision problem is uncountable. So, this is the bad news. So, there are many problems, I mean, so there are many problems which cannot be solved by the computer program, and that means that is, so there is no finite number of steps we can solve this. So, these are uncountable, these are beyond R, because our computer problem is basically a given problem can solve one particular, given program can solve one particular problem. So, this set is n, this set is R, this is very big set. So, that is the bad news, we have many problems which is unsolvable. Okay. So, in the next, we stop here, in next class we will discuss the more notion like NP hard, NP complete. We will continue in the next class. Thank you.